In this video, we are going to talk about battery management, schematic and PCB layout, and we are going to be very specific. Erik is going to explain his open source project. So what we are going to learn today, this circuit, what you have on your table?
Yes, so this is Tiny Guard. It's a power management. It's a module which targets single cell rechargeable batteries. It has a lot of features in a really small footprint. You can charge your battery. You can monitor its output current. It has a built-in MOSFET for powering high power loads. It has a 4-channel dedicated ADC and a few more features, everything that's needed for single cell battery management.
Okay, and as I said, okay, we are not going to learn how to design it, but we are going to talk about the design. So if anyone who would like to design this by themselves, they know how to do it. They can do it based on your schematic and based what we are going to talk about. Okay, so I think we can start. First, let's have a look how it works and what features are supported.
Okay, so I have a little demo set up here. It's basically everything's running on the Bed Tiny Guard module, so there's like no external components needed. So I have two fans here, uh, two push buttons, three LEDs, potentiometer, and a few wires and other small components. So the demo circuit basically does the following. We can turn on the fans.
The fans are the load. Yeah, they are connected to output.
Yes, exactly. The fans are the load, and they are connected to the battery output, or better yet, through the MOSFET, which controls the output of the battery. So we have a few measurements and a few key information points on the screen here. We can measure the current of the total current of the output. We can measure the battery voltage, the module temperature, uh, whatever voltages are connected to the ADCs, and a few other things.
So I'm
So,
going to interrupt you. So basically,
okay.
we are not using any kind of like standard battery management chip, but you implemented everything inside of a microcontroller.
Yes, that's correct. So everything is implemented inside the microcontroller. Basically, this is because it leaves a lot of room for customizations, and in my previous projects I had to customize a lot of stuff, to make it work with the components I had, or yeah, I plan to use. So you can reconfigure every single aspect of the battery management. You can set up, I don't know, to shut off the battery output at, let's say, 15 milliamps, or whatever arbitrary current you want. So basically the module leaves leaves a lot of room for customization.
And how do we? This is the serial output from the microcontroller, correct? What we see in the terminal.
Yes, that's correct. So this is the serial output from the microcontroller. So basically, it's generated on the microcontroller itself and just displayed on the computer. Uh, this is just the information that's needed for what I have connected, but there's a few other measurements that we could take on the module itself, like other 3 channels of the ADC, or the battery current measurement, shunt voltages, and a few other detailed informations that aren't available here.
Mm-hmm.
But so
No,
I
no,
I
I'm
can.
going to again interrupt you. Sorry. So we will go back to demo, but I would like everyone to understand what we are looking at. So basically, in the demo, there are two boards. These two boards, what you have on the left side from your board, correct? So the module is the core, that's the battery management itself, but you also have this breadboard, which helps us, for example, to connect this terminal, which we use to show the values, correct?
Yes, that's correct. So these are basically the two boards. This one isn't populated, but this module goes on the breakout board, and it's all connected into this one single breakout. The breakout doesn't have anything special on it. It just has the USB connector and the USB to TTL converter for the programming and serial communication.
Mm-hmm.
The header's broken out, and that's pretty much it for the breakout board.
Mm-hmm. We will have a look on the schematic a little bit later of the breakout board too, so everyone will see what is there. And also, I think maybe what we should show, where is the battery?
Yeah, the battery. So it's all powered off of this battery. It's connected. I soldered the wires directly to the breakout module, but you can use the connector or any other means of connecting it.
Okay, and what is the big black, what is capacitor? What is it?
Yeah, so the demo actually works without it, but the fans sorry,
Oh, yeah.
the fans behave little bit more smoother with the capacitor.
Mm-hmm.
It's not necessary, but I put it on just so the fans start up a little bit easier.
Okay, perfect. So now you can explain the features. So basically, you can switch on the power when you press a push
Yeah,
button, correct?
yes, that's right. So I have this push button right here, which if you press it, you can switch on the output.
And we can see also the current increase.
Yeah. So when it's switched off, it's about 10 to 15 milliamps. And this is important to note. When the fans start, they draw significantly more current than when they're running. So we seen a measurement of 150 milliamps. The current actually went significantly more than that. We have this relatively big capacitor to charge, so it needs a bit of current to charge up. Actually, in the code, there's like a filtering function which ignores the startup current, so it doesn't go like straight into fault mode.
Mm-hmm.
Uh, but yeah, it's one of those things that you don't think about until you meet it in like real life applications.
Yeah. And then we have
Uh,
green LED. I guess that means everything is
yeah.
working okay.
So the green LED means everything is working okay. We have a yellow LED, which is like a warning condition. So, if we go between 100, I think I have in code set up like 120 milliamps and 160 milliamps. So that's the warning LED. We can see it turn on here if we stop one of the motors by hand. You
Mm,
can
oh
also
yeah,
see
it's green and yellow
yeah,
together.
you can also observe the current on the serial
Mm-hmm.
monitor rays. And if we stop both of them, the output shuts off
And it's
because
red.
yeah. So red means we enter the fault condition and the output shut off.
Mm-hmm. And fault
So
condition because current was higher than
yeah,
threshold, what we said.
yeah, the current was higher than the threshold. Currently, the threshold is 160
Mm-hmm.
mil. We can change the threshold with this potentiometer, so we can increase it. Let's increase it to the maximum. It's 250 milliamps. Let's reset the fault condition.
Oh, that's the second button. I was thinking why there is the second button.
Yeah, so the second button resets the fault condition, so we can start back again the output. So now, if we stop one fan, we still get the yellow LED, but we increase the threshold to 250 milliamps,
It
And
doesn't go
now
to error. Yeah.
yeah, it doesn't go to there because we're measuring 177
Mm-hmm.
milliamps. And if we release it, it will just
Mm-hmm.
go
And
back again.
threshold is 249. I can see it there.
Yeah. So if we stop both of the fans by hand and move the potentiometer slowly until we get the fault condition like this. So
Mm-hmm.
we now have like we can observe on the serial monitor the exact point at which the fault condition occurs, and
Mm.
we can reset it, start it back up. So now we have like the exact point at which we can trigger the fault condition.
Perfect.
And
Yeah.
yeah, that's pretty much it for the demo. Yep.
Okay, so now let's have a look on the schematic, then on the PCB, and let's learn how everyone can actually do this. So first, I think first we should mention where people can find the project.
Yeah, people can find the project on our GitHub page. It's all open source. Basically, it's under my company name. So the company name is EDR Tech. And we have a lot of more projects, but this whole project is up on GitHub, and all the source files, everything that was used for development is included, so you can modify it in any way you want, make anything of it, copy it, sell it. You can do whatever you want with it.
Learn from it.
Yeah, learn.
Okay, and the source files, you told me original source files are in Eagle, and then you also
Yeah,
imported it to KiCad.
yeah, original source files. So the original project was done in Eagle, but I converted everything to KiCad. Unfortunately, the schematic doesn't look the best it could in KiCad because conversion process and that stuff, but it's readable, and uh, you can still understand what's happening in the whole module.
If we go to the GitHub, what can we just go through the directories? I'm just
Yeah.
curious what is there.
Yes. So in the GitHub repository, we have the source code. Well, basically the source code for the demo. We have like the fan demo code.
What is inside? Go there.
Okay, so it's basically a Arduino IDE projects.
Okay.
So you can download the directories and modify them directly.
Okay. Perfect. Perfect. Then what else is there?
Okay, so these are the source files for cutting out the small breadboard
Mm-hmm.
board folder. We have like documentation, so we have like assembly files, so everything with like the components listed, which are not listed on the board itself, so that's needed for the assembly. And same thing for the module,
Mm-hmm.
the values and names of the chips. We have bill of materials. Well, I don't have to open that right now. Footprints that were like new on the module. Schematics in PDF format for both the module and the breakout board, and the like a lot of images of the
Mm-hmm.
of the modules and that stuff.
Okay. Okay.
So for the source files of the boards themselves, we have separated the breakout board. We have like the separate Gerber files that were used for production. We have the KiCad conversion and the module source files separately, and also we have the layer files, which are basically the same as in Gerber files. So all all the layers are listed in these PDFs.
So if someone would like to just buy it, if they don't want to design it, do you sell it?
Yeah, so the plan is to sell it, but at the moment we're running uh, a, preparations for a crowd supply campaign. So you know, you can check out the crowd supply page. Well, it's pretty much the same as the GitHub page, but you can subscribe there, leave your email, and be notified
Do you have it
once it's
open?
available.
If someone is
Uh,
interested.
yeah, we can go here.
Okay.
Yeah, so it's basically the page, basic information about the project and few images. If anyone's interested, you can leave your email here and you'll be notified once the campaign actually starts. So at the moment it's in the pre-launch phase.
Okay, and I would like to point out when we talked last time together, you explained why you actually designed this circuit. So you can tell it because I think this is also interesting to consider.
Yes, so as I work, developing electronics. Most, if not all of my projects are based on single cell rechargeable batteries. So for every project, I had to redo the power management part, and it's not difficult, but each project has like some little specific things that you have to change and adjust for it. So I thought about making a single module that I could just use it as a standard component in my component library and just put it as is on my projects, and do a little bit of programming on it to make it work with a specific project. And that's pretty much how I got the idea. And it's based on well, a few designs I found to work best for me or my applications. So that's how I got the idea for the module itself. And I'm actually using it on a few different
Projects or
projects.
boards, yeah.
Yeah. So this is like an internal testing tool. It's used for testing rechargeable batteries. It has a bunch of resistors to discharge the battery and a few other things to control it. And I use it on a few bigger PCBs for managing power. And mostly for me, I use it as a step before a buck boost regulator that powers like the rest of the circuit downstream, let's say.
One more,
Uh,
or maybe two more questions. One more question before we have a
yeah,
look on the schematic. So, what are the parameters? I'm curious. Input voltage and the maximum current.
yeah. So the input voltage is up to 5.5 volts. It would probably tolerate a bit more, but it's officially it's rated up to 5.5 volts. And the currents I have tested, like the battery output current or the current that is measured and outputted through the MOSFET, was tested at 7.5 amps. Yeah,
Okay.
so that's at the maximum battery voltage or of 4.2 volts.
Okay. Let's have a look on the schematic. I'm curious. How does it work? Where is the microcontroller? Ah, I
Okay,
see.
so yeah, so it's all based on ATtiny 1616. Uh, it's basically it controls the whole module. There are some hardwired things like
If you like, we can use PDF. You said PDF may look a little bit better.
yeah, it may look a bit better. Just let me. Uh, yes, this is not the one. Just a second. Let's do this.
Mm-hmm.
Just download it so I can zoom in.
Okay.
More. Okay, yeah, this looks a bit better. Okay, so it's all based on the ATtiny 1616 microcontroller. There are a few built-in functions that take up some of the pins, but I try to keep that to a minimum so the user can use the most pins that are available. The circuit itself, basically, it works. It's all powered by the connected battery. The battery is connected to a 3.3 volt regulator, which powers all the ICs and the microcontroller. And there's also a, a power on reset circuit, which and also it has a built-in brownout detection, which will turn off the whole module if the voltage falls. I think it's under 2.8 volts, because that's like the safety limit for rechargeable lithium rechargeable batteries, which really shouldn't discharge them under that level.
Mm-hmm. So the
So
LD56100, that's the
yeah,
regulator
yeah,
from
that's
battery voltage
the
to 3.3 volts.
yes, exactly.
So
So it's
if the battery voltage is lower than 3.3, it still can handle it.
yes, it will work to 3 volts. So the regulator will let like full 3 volts go, but under that, it may start misbehaving and causing issues. So like the parameter is like the battery shouldn't go under 3.3 volts, under normal working conditions.
Okay, okay.
Yeah. So for that reason, we have the brownout detection, which will turn off the whole module if you know any if the brownout level is reached. Uh,
Where is battery? Where is battery?
yeah. So the battery, it's not clearly
Oh,
marked
I see
here,
label
but it's
battery. It says
it's connected here. So basically, this is the positive terminal of the battery, and this is the negative
mm-hmm.
terminal. Yeah. So we have the battery charger.
Mm-hmm.
It has two LEDs, a green LED and a red LED, which indicate on the module itself the status of the battery, if it's charging or if it's fully charged.
So these are not the LEDs what I seen in the demo. Yeah,
Yeah, so these are the LEDs on the module
I
itself.
see there is
So
green LED on the module.
yeah,
Yeah.
yeah. So the module has three LEDs, one for the fully charged state, one for the charging state, and one for the built-in LED. In the demo code, the built-in LED just shows if the output is enabled or disabled. So, but the user can program the LED to do, whatever they need it to do. Yeah, so we have the output MOSFET.
Mm-hmm.
basically this symbol right here. It's DMP 301 3SF. I don't think the full marking is important, but it's a high power MOSFET. And as I said, I've tested the module to let the current of 7.5 amps. And as long as you can keep the module cool, it will run that current continuously.
Oh, okay. So now I understand. So the regulator is only for the internal 3.3 volts, and the battery
Yes,
out, that's the output which is going out from the module.
yes, that's correct. So the battery output goes through the shunt resistor, which is used for current
Mm-hmm.
measurement, and it goes to the output MOSFET and to the output pins of the module.
Mm-hmm.
So basically, you can power high power loads from using the module, which is the main point of the module. So the main high power MOSFET has a driving MOSFET. I had to include the driving MOSFET to ensure the when the module is powered, uh, microcontroller pins can go all around the place, and we really don't want to power the main MOSFET on accidentally, you know because all kinds of bad things can happen if you do that. So to ensure that, it has a dedicated pull down resistor and for the driving MOSFET, so we can
So by
rely
default, it's
on it.
basically off, and then we can wait
Yes.
until software will initialize microcontroller, and then you can control the pins.
Yes, that's correct. By default, it's off, so it's a fail-safe feature. So if anything goes wrong, it will shut off. So that's the safest way to do it, basically.
Mm-hmm. And IC9, I guess that's AD converter or something.
Yeah. So we have an ADC.
Oh, I mean the other one. Where is the shunt resistor? Yeah.
Oh, yeah. So basically, it's an I squared C current measurement IC. Basically,
Oh.
it's measuring voltages on both sides of the shunt resistor, and calculating the difference, and calculating the shunt voltage, and it's also measuring the voltage on one side, and using that to calculate inside the IC what the current is. And you know we can basically read the finished measurement from the
Chip directly.
yeah,
Oh, this
exactly.
is interesting. I didn't know something like this exists. Okay, so this is like chip dedicated for current measurement with this specific resistor.
Yeah, well, different resistors can be used.
But you need to set it, I guess.
Yes, every time you run the IC, there's like a setup step
Mm-hmm.
in which you input like the input parameters, so the IC could calculate everything and output the correct measurements.
Mm-hmm.
Uh,
Okay. So now we can go back to the standard ADC. So that's like the microcontroller. It doesn't have ADC, or why did you
yeah,
use a different
the
one?
microcontroller has well, I think eight ADC channels. I might be wrong. It might have a bit more channels, but why I used it is because of the performance,
Mm-hmm.
basically. So the biggest issue is if we're powering the module from something around 3.3 volts. So if it's a bit lower, the reference voltage for the ADC
Mm-hmm.
in the microcontroller is not going to be consistently the same. So that's why we use a dedicated ADC IC, because it has an internal reference,
Mm-hmm.
so we can keep the measurements correct all the time.
Mm-hmm. So where is it connected? I guess it's
Yeah,
measuring the voltage.
yeah, so it's not connected to anything on the module itself.
Oh, okay.
The pins are just broken out. This is because, if you want to measure like the battery voltage or any voltage on the module itself, you can easily just route a few traces under the module, connect a few of the module's pins together, and make the measurement. Instead of making it like a design choice to have a few channels connected to something on the module and only to that.
So the input voltage or the voltage of the battery is measured also with the IC9.
Yeah, so
Okay.
the voltage of the battery is measured by the INA
Mm-hmm.
12
Mm-hmm.
19 chip. So that's an integrated measurement of that
That's a
IC.
cool chip. Oh, I have to remember this one.
Yes, it is. It can. I don't remember what's like the maximum current it can measure, but I think it's like
Can
15
we
amps.
open datasheet? I'm just curious.
Yeah, I can find it.
Oh, okay.
Yeah, I got it now. Okay, so here
Oh, digital
it.
power monitor. Mm,
Yeah, so it can
26
sense,
volts.
yeah, up to 26 volts. It's 0.5% measurement error. It's a nice IC for this application.
Scroll a little bit down. What are the registers about? What kind of register it has?
Let's see. We can go from here.
Little bit down. There will. Ah, here is.
Okay.
On the top. There was the all register. Okay, here. Okay.
Yeah,
Okay.
so
Go
we
down.
can
Power and current. What is there?
we can input the parameters and the IC will calculate the current and output it in a proper format. Shunt voltage. So this is basically the table of how the registers would look on readout.
Okay, we can go back to schematic. If anyone is interested, we'll look on this chip. It looks very nice. This chip looks very nice. Okay, then IC5. That's
Okay,
what temperature sensor.
let me just go back to
PDF.
this is okay.
Okay, IC5.
Yeah, so IC5 is a digital temperature
I was
sensor
guessing.
sensor IC. It basically works on through I I2C. It basically provides an accurate temperature measurement of the module itself. So you can use that, since you can run such a great current through the module. It's a smart feature to monitor the temperature and watch out for like over temperature
Hmm.
conditions and things like that. So uh, basically, it provides an accurate temperature reading of the module itself.
Hmm. I see you didn't connect the alert, so I guess your microcontroller keeps reading temperature all the time, correct?
Yes, the microcontroller reads the temperature and makes decisions based on the
Hmm.
reading.
Okay, what is on the left? Ah, that's
Yeah,
the charger.
yeah,
Okay.
this is the charger and the supporting the supporting circuitry. This is the inductor. It's like the biggest single component on the module itself. It was a real challenge to find an inductor that small that can withstand the currents needed,
What
and
else
also
is there?
not heat up that much. Yeah,
I think that's everything. Is it everything?
yeah, that's pretty much it about the module itself. Basically these are just the castellated hole pins broken out, and yeah, that's pretty much it for the schematic.
Okay, let's have a look on the breakout board.
Yeah, okay.
So a lot of secret is actually, or a lot of work is actually in the software, correct?
Yes. Well, a lot of it is in the software because I wanted it to be like really flexible, and so it can apply to a lot of applications. Basically, if you want to change, like if you want to use the module just for on-off behavior handling, or if you want to like actually measure high currents or measure a few different voltage rails, and you can make the decisions based on the measurements from the module and turn the whole system off, or throttle it or anything in between.
Mm-hmm. Okay, so
Yeah,
this.
so this is the breakout module schematic. It doesn't have anything special on it. Basically, it has the USB-C connector. It has a USB to TTL converter,
Mm-hmm.
and this is a small circuit that switches between UPDI programming mode and serial communication mode for the AT-Tiny 1616. Uh, this is needed because there's no official support for serial over UPDI in Arduino IDE or Mega Tiny Core, which is basically the library for the AT-Tiny 1616 if you want to use it with Arduino.
So this is basically also kind of programmer.
Yes, this is a programmer. Basically, this is this part of the circuit, like a diode and a resistor, is everything that's needed for programming the microcontroller.
Okay.
And yeah, there's an analog switch which switches the serial lines between the UPDI and serial.
Mm-hmm.
And yeah, that's pretty much it for the breakout
So it
module.
means on the microcontroller there are three pins, correct? The one for the programming and then a serial console, and with this switch you switch between these pins, which are
Yes,
connected
exactly.
to the serial port to USB converter.
Yes, that's correct.
Mm-hmm. Okay, perfect. Let's have a look on PCB. I'm
Okay,
very curious.
we can
Model
open
PCB. Okay.
module PCB. So yeah, so this is a KiCad conversion. So there might be a few things that are kind of weird, like these connections here,
Mm-hmm.
but that's a result of the conversion. Uh, yeah, so this is the top layer of the PCB. Uh, yeah, so everything is, it's like crammed up in the smallest space possible, and there wasn't really any room left if I wanted to keep the form factor like this. There wasn't any room to add, well, pretty much anything else,
Mm-hmm.
at least in the packages that were available.
I see you use VIAs in path exactly for this reason, I guess.
Yes, so a bit about the PCB itself. It's a six layer PCB. It's a VIA in pad PCB. Yeah, so it's mostly routed on a few layers. Basically, what?
Well, let's go on the top. I'm curious. So on
Okay,
the
yeah.
left there is the microcontroller, I guess.
Yes, this is the microcontroller.
Okay,
This
then
is
next.
the ADC.
Mm-hmm. ADC, that's the one which is kind of free to use for
Yes,
okay,
yes,
for measurement.
that's right. So, and if I'm seeing correctly, this is the current measurement ADC or IC. This is the regulator, the
Mm-hmm.
smaller one on the bottom left. This is the temperature sensor.
Mm-hmm.
So it's placed close to the shunt resistor, basically, which is the the shunt resistor and the output MOSFET are like
Mm-hmm.
the single two components that heat up the board the most. Well, at least when the battery is not charging. When the battery is charging, then the charging circuit heats up a bit.
Oh,
But
that's the charging circuit here.
yeah,
That's the
so
inductor.
this is the inductor,
Mm-hmm.
and this is the charging IC.
Mm-hmm. Okay, what is on layer two?
Yeah, so layer two is reserved for power mostly. So this is a complete plane for the
Can you
battery.
select the planes, or the selection doesn't work after the import? Or
That's it's not working for some reason. Let me see. Just a second.
maybe
Oh,
filter
I
like all
I
items, selection filter all
I
items.
couldn't see it. Okay.
Okay.
Yeah. So this is the battery power plane,
Mm-hmm.
and this is the output battery power plane. So, and this is the 3.3
Mm-hmm.
volt power plane.
Okay, next one.
So basically, this whole layer is used just for power.
Mm-hmm.
Uh, layer layer three is used for a ground plane and a few signals.
Mm-hmm.
So these,
That's these are the signals from the resistor, shunt resistor.
yeah, these are the signals from the resistor, and so that their distances had to be kept like pretty close to each other. So basically, the you get like the best measurement on the shunt resistor. So both of them are going with vias to the top layer and connect in the same way to the pads of the shunt resistor. So this is quite important for the IC to get like the correct measurement. Uh, Yeah, so the unused space on this layer is filled with a ground plane. It could have been left empty, but it's always better to use a ground plane. So the next layer has a few signals,
I guess
and
these are mostly from microcontroller. Yeah, I can see.
yeah, these are mostly from the microcontroller, well broken out to the castellated pins or pads. These are few auxiliary for the resistors and stuff like that, and this is a dedicated ground plane. So this one is completely unbroken by traces, at least. As you can see, it's broken up by vias, but since I couldn't really use blind or buried vias, it's something that I just have to live with. And for the bottom layer, we have we have a power plane for 5 volts input from the USB, or you can input 5 volts from anywhere. It doesn't really have to be USB to charge the battery. And this is also the second power plane for the battery output, and the rest is a ground plane. on the bottom layer. And yeah, that's pretty much it for the PCB itself. We can go back to this layer.
When we are talking about this, I'm curious about manufacturing this PCB. So, where do you manufacture it? Because of the castellated holes, did you have to specify something, or are there any troubles? Or I've seen people asking about these castellated holes. Maybe we could explain what it means. I'm not sure if everyone knows what it means.
Yeah, so castellated holes are basically connection points that are done in the PCB manufacturing process itself. So they don't require like any extra components to be connected to other PCBs. Basically, what castellated holes are, they are plated through holes, which are milled in half. So, like half of the plated hole is cut off and left exposed on the edge of the
For
PCB.
the soldering, for example.
Yeah. So you have the plated part of the hole on the edge of the PCB, and
We
you
can
can,
search on internet, or maybe if you have detail so everyone knows. But
yeah, we can find the. So this is an example of another module.
oh, up, go up. On the right, on the right. Yeah, this. Yeah, it's nice
Yeah,
one. Yeah.
yeah. So it's clearly visible on this. So they are plated holes that are milled in half, so they are accessible from the PCB sides.
But I know you need to say they are castellated holes because they need to maybe make it carefully somehow so it doesn't peel off or something. I don't know.
Uh, yes. So with the manufacturer I use well mostly JLC PCB.
Hmm.
Uh,
Then you have
I
to
don't.
check it. I think they have checkbox or something.
Yeah, you have to check the checkbox for the castellated holes, but from what I understand, it's only because they do like a manual inspection step and like manual workup on the
Hmm.
castellated edges if there is like some tearing or some excess material or something like that.
Hmm.
Yeah, from what I understand, that's basically just for that. So
Hmm.
it does cost a bit extra, but it's not like a huge difference in the price.
Oh, so actually you use their 6 layer via impact PCB. They send me a couple of emails like if I don't have projects for this kind of PCB because they would like to they would like many or more people use it. I was like, but it has to be something really small. And yeah, exactly this project.
Yes, so this 6 layer stack up is like it's really well suited for this small project because well, I guess it could be done on 4 layers, but it would require much more time for routing and component placement than it required for 6 layers. And actually I think JLC uh, offers free via embed for 6 layer PCBs.
Yeah, I
So
think they
yeah.
have something special there. Yeah, I know. Uh, okay. So what were the when you were building this circuit or designing this circuit, what was kind of tricky, or what you improved later, or something like this? You found out like, oh, this doesn't work as I imagined for first time, or
Yes, so well, there's one thing that I'd like to mention that I at the time when I was designing it, I just couldn't route it properly, so it works. Let me open the schematic so I can show it. So basically, it's this shunt resistor part. Uh, as you can see, it's placed down from the battery charger. So the basically it doesn't measure the current that the battery is charged with over the shunt resistor. So that current doesn't pass over that
Mm-hmm.
resistor. This is because I tried like 4 or 5 times to, place all the components and route them carefully. I lost over 14 or 15 hours just to try to do it so I can measure both of them, but I couldn't place the components or route it properly to get it set up that way. So that's like one thing that I still haven't managed to correct.
But then
Uh,
where would you need to place it if you would like to measure also the
yeah,
charging?
so it would have to be placed like rotated, and basically all the components would have to be like moved downwards, and there was just no way to connect basically all the high power traces
Mm-hmm.
wouldn't have enough space to handle nearly as big current as they can handle right now.
But in the schematic, where would you place it in schematic?
Yeah, yeah, it would be placed basically, well, here above this junction.
But then it would it measure also charging current?
Yes, it would, because the charging current, well, basically it would go through the inductor and over the shunt resistor to the battery. When at the moment it goes directly through the battery. This IC
Oh,
can
okay, oh,
measure,
okay, I understand now. Okay, sorry,
yeah, this IC can measure in like both directions, so that's not the problem.
I
The
understand now. Sorry, I
Yeah,
understand.
the real problem was I just couldn't get it routed properly in this small space that I had to work with.
Mm-hmm.
Yeah, and the other issues we mentioned already. This just wouldn't be possible without via in pad, and well, a lot of layers.
Okay, I think
Well,
I
I
ask
had to,
everything. Yeah, go ahead.
yeah, so I had to, at some point I was updating the design, adding the driving gate driving for the power MOSFET. So I had to use like a really small BMP package for that MOSFET. It was a challenge to solder, but worked out in the end.
How do you solder it? Do you solder it after you receive boards, or you ask JLC to solder it?
Uh, I assembled them. I assembled the boards myself. So basically, paste, stencil and paste, and placing the components with tweezers one by one by hand.
Do you have oven or you use the plate, hot plate?
Uh, I have a small reflow oven, and I use that mostly. Well, for these smaller modules, I use like the USB powered reflow plate
What
for
is
these
your
smaller.
experience with the plate? Because I would like to actually make video about this one because I bought the 5 by 5 centimeter. I forgot MH something it's called or something. The hot plate, and I'm like, okay, maybe it's useful, but only if there are components only on one side and only for small boards. Otherwise, nah.
Yes, exactly. That was just the issue I ran into a few days ago. I had a small board. Well, it was about this size, like the bed tiny module, and I put it on the plate, did the components on one side, and then I like put the components on the other side, and I was thinking, but if I put the board on the plate, then there's like not enough surface area to conduct the heat, and it just wouldn't work. So yeah, if you have components on both sides, those open air plates, as I call them, they're often they don't help that much.
You could, what I sometimes do, I use nuts. So you use nuts in the corners and then you lift up the board a little bit. It still can heat up if it's like 1 millimeter above the plate. But the components which are just between the plate and the PCB, I think they will have much higher temperature than the components which are on the top.
Yes,
So I don't think that's the
it's
best way
it's
to do it.
well, it all works out when you don't have like some plastic components, something that doesn't handle heat that well.
Mm.
But if you have those like connectors and stuff like that, yeah, then you're gonna melt those before you reflow the board.
Yeah, I need to make video about this because I know one time it was very popular, especially the MH something, I don't know. All it was all over the YouTube, and I was like, I really want it, I really need it. It looks so useful, but I couldn't find a project for this. But a little bit later, I had a project where I could use it, so I bought one, and I was disappointed. I was like, I should buy the hot air uh, soldering station rather than the plate.
Yes, the hot air gun or the station is, much more versatile and
Exactly,
useful
exactly.
all kinds of rework or assembly
Okay,
tasks.
okay. So maybe a little bit about yourself or about your company. What do you do?
Yeah, so uh, I have a company that works on electronics development mostly for the educational sector. And well, I make electronics for teaching how electronics themselves work, and how other concepts like mathematics and basically anything that electronics can be connected to work. So that's mostly what we do. uh,
You have a website?
yeah, I have a website. Just a second, I have it open here. I think, yeah, it's here. So this is our website. uh, there's basic information, about this tiny project, about some other projects we worked on. And yeah, if anyone needs any help with educational and electronics or electronics development in general, well, you can see I can make like pretty small boards. And yeah, that's pretty much it about the company.
Okay. I know you didn't want to talk too much about your company, but
Yeah,
I'm very happy always to also provide some kind of background information for everyone who is on my interview videos.
yeah,
At least
that's
that's
that's okay.
something what I can do. Give you back for spending time preparing this project and talking in this video. So thank you very much, Eric, for sharing this circuit, and I really hope some people will find it useful. For me, the most interesting was the chip for the current monitoring. I may use it maybe. So
Yes,
thank you, Eric.
thank you, Robert, for inviting me, and I hope everyone learned something, and they can base their own projects and battery management systems off of my project.
That's all for this video. I hope it was helpful. If you would like to learn more about electronics and board design, check out our online courses. You will find everything important there, from basic board design up to advanced board design and high-speed PCB layout. We have courses in Altium, Cadence, KiCad, and also courses covering many different topics, for example, FPGA, EMC measurements, and so on. Visit our website at fedevel.com. That's all for this video. Thank you very much for watching, and don't forget to leave your comments. See you in the next video. Bye.